This video we're going to work a simple problem using application of all the possible ways you can use LeChatelier's principle. And we're going to use this chemical reaction between nitrogen dioxide and a mixture of nitrogen oxide and molecular oxygen. Okay, and so when you place a stress on an equilibrium and shift it out of equilibrium, then the forward and reverse rates will no longer be equal. So if the forward rate is now greater, then we say the reaction shifts to the right, because to the right is forward rate being larger, and so that means a net forward reaction. So we'd say shift right. If, on the other hand, the equilibrium has a larger reverse rate, then we'd say it shifts left, because going from product to reactant is the arrow pointing to the left. Okay, so let's just apply all these. So we talked about how to add and subtract something, but let's go ahead and practice that. If we add NO, we add here, the system responds by removing it, which it does by going that direction. Another way you can kind of remember, if you add something to one side, then it shifts the other side. Okay, so if we add NO, it goes to the left. So it's also useful to use the word left. Now, what about temperature? Well, that's a little different. This is an endothermic reaction. Remember, there's two different ways to write endothermic reactions. One is delta H as a positive number, and the other is to write heat as one of the reactants. Well, if you decrease the temperature, you're going to remove heat. And if you remove heat, it's like removing one of the reactants. If you remove a reactant, it goes to the left as well. Okay. Now, this particular application of LeChatelier's principle actually works by not necessarily having the same equilibrium constant, but the reverse rate will be greater, and what that means is actually the equilibrium constant is going to change on you. But we won't concern ourselves with that particular detail. All we want to know is that as you remove heat, as you lower the temperature, an endothermic reaction becomes less and less favored. This is also to the left. Okay, removing O2, we're removing the product, and so it's going to shift right. Okay. Increasing the volume, we'll do in a minute. Removing NO, if we remove NO, it'll shift to the right. Now, one of the trickier ones is changing the volume. If you change the volume, you're going to change the pressure. And if you change the pressure, you're going to change the number of collisions between the gases. And that's going to have an effect if there's more gases on one side than another side. So what happens is that if you expand the volume, there's now more room for molecules to kind of move around in. And that favors the side with the more moles of gas. And so increasing volume favors this. So it will shift to the right. The other way of thinking about this is if the collisions depend on the pressure, if we increase the volume, we're decreasing the pressure, we're decreasing the number of collisions. Well, this is more affected by the number of collisions than this is, because this only depends on two molecules hitting each other. This depends on three molecules, not hitting each other all at the same time, but hitting each other. And so the number of collisions go down as the square, but the number of collisions goes down as the cube here, and so the reverse rate is very much slowed down compared to the forward rate. And so that's why the forward rate is larger and shifts to the right. Okay, that's it for using LeChatelier's principle for changes in volume, changes in temperature, or adding or removing reactants or products.